So I want to show you a couple of examples on qualitative analysis, and next to provide some interpretation. And the next step will be to see a few basics of difference equations, which means dynamics in discrete time. Okay, can you hear me at home? Is everything okay?
Yes.
Thank you. Thank you. Okay, so let me show you this example. This is a mathematical example in which we have to study the properties of a dynamical system in continuous time, only based on the qualitative analysis. Next, I will provide some interpretation, okay? So suppose that I want to study the dynamics of this equation. This is a differential equation, y dot, y is a variable, is y of t, is equal to a positive constant k is positive, minus y, which is the same variable, this is the derivative, time derivative, this is the level of the variable, to the power of minus alpha. Alpha is a positive quantity, so this is a negative exponent, which means k minus 1 over y to the power of alpha, okay? And of course, what we want to understand the behavior and the range of y, which is relevant for our analysis, is positive y, okay? Of course, y cannot be 0. It can be negative in principle, but what I'm writing here makes sense for positive y. Y cannot be 0, of course. Okay, so to study the qualitative behavior of a differential equation, which is autonomous, you see that the dependence on t here doesn't appear explicitly. There is some dependence on time, but it's only through the level of variable y, okay? So there is no explicit direct dependence on time. It's autonomous. Otherwise, we cannot study the qualitative behavior with a phase diagram. I want to show you how to understand the behavior of this. Suppose, for instance, I want to represent this function, okay? So 1 over y to the power of alpha, or y to the power of minus alpha, if you remember the elementary functions, is something like this, okay? It's negative, it's something like this. Okay? And look at the negative, minus y to the power of minus alpha. If y becomes larger and larger and larger, then this one tends to, it remains negative, but it tends to 0, okay? So if you add k, which is a positive constant, you basically shift everything upwards by an amount equal to k, which means that since when y tends to 0, this goes to minus infinity, okay, because it is an elementary function. Here it goes to plus infinity, here to minus infinity. If you add a positive constant, it goes to minus infinity as well, but at some point it will cross the axis, the x-axis. Unlike this one, it will cross the x-axis and then it will go asymptotically towards a value which is k, okay? And what I'm representing here is the whole function here, okay? K minus y to the power of minus alpha. Is that clear? So the exercise asks to study, to determine the steady state to conclude graphically about its stability, by means of the so-called arrows of motion, so by means of the qualitative analysis. You know that the steady state satisfies y dot equal to 0, which means k minus 1 over y to the power of alpha equal to 0. Which basically means trying to understand where this curve intersects the x-axis. Graphically, we see the steady state here. So here is, of course, what is represented here, k is just the level of the constant, k here. Here we have y, and here we have y dot. A phase diagram represents y as a function of y dot, or y dot as a function of y, or x dot as a function of x. So we represent a function, but the meaning, the practical meaning of this function is the trend of the variable as a function of its level, okay? So this is the meaning of the phase diagram. Okay, so the steady state is here, it's y star. And we can determine the y star also analytically, because 1 over y star to the power of, or 1 over y to the power of alpha is equal to k. So y is equal to 1 over k to the power of 1 over alpha, okay? So remember that these types of simple equations involving the power of the variable, often a negative power of the variable, are very common in economics, growth theory. So there are simple models represented by power function where you want to find a maximum or a steady state. You have to solve some power function equal to a constant, okay? So this is the solution in this case, okay? So this is y star. 1 over k to the power 1 over alpha. So for instance, if alpha is, here is 1/2, here becomes raised to the power 2, okay? And k is the constant. Now, is this steady state stable or unstable? We see that it is a monotonically increasing function. It crosses the x-axis, it's called the y-axis, but the horizontal axis, from below, and as a consequence, the arrows will be like this. And the reason why the arrows will be like this is that on the right of y star, the time derivative is positive. And this means that the quantity will increase over time. On the left of y star, the time derivative is negative, and our quantity will decrease over time. And it is clear that the movement will be away from the steady state. Okay? Interesting interpretation. I mean, mathematically there is nothing, this is a power function, okay, plus a constant. But of course, simple ideas rely on simple functions. So there is an economic interpretation which is interesting. Suppose that y, which is, remember that you have typically here, so this is a flow because it is a time derivative, okay? This is a flow. Typically, the flow depends on the amount of the stock, which is the level of the same variable, and some other, if there is some other constant here, this is a rate of another flow, okay? So here, the nature of what you see here is time derivative. So these two components are flows, okay? Suppose that y represents the amount of pollution, let's say CO2, for instance, in the atmosphere, okay? Y is the stock. K, which represents the flow, flow is the level, that is the intensity of emissions per unit time. This is the intensity of emissions. Y is the level of the pollution. In general, this can be interpreted as pollution, but not only pollution, in particular CO2. Okay? What does this equation tell us? This is just a model, it can be acceptable or not, but what is the meaning of this model? You have here, let's say, the stock of CO2 has some degree of spontaneous degree of decay, okay? So if you don't introduce any new emissions, there is some decay of the stock of CO2, for instance, due to the absorption capacity of the environment, forests and so on and so forth, okay? So there is some degree of decay. So this is a force that in the absence of K, if K is 0, tends to reduce, okay? Because the derivative in the absence of K would be negative, okay? So the stock of pollution will decay over time, thanks to this factor. But, on the other hand, we are at an intensity of emissions at each point in time, okay? So a force that tends to increase the CO2 and a force that endogenous force that tends to decrease this amount. So in this model, the natural rate of decay is modeled in this way, which is, I think it's interesting because 1 over y to the power of alpha. So it says that it is something that depends negatively on the stock of pollution, okay? So there is some decay rate, but the larger is the stock, the smaller is the decay rate, okay? There is some effect of saturation, okay, here. This is a possible model. We could have different models, but let me see what this model implies, okay? So this is the model. We see that we have a steady state here. This is the equilibrium level, let's say, steady state level of CO2 in the atmosphere, but it is unstable. This means that normally, unless we are exactly here, normally the amount of CO2 will tend to increase, or the amount of CO2 will tend to decrease if we start respectively on the right or on the left of the steady state level, this critical level, okay? Is that clear? This is the interpretation. So for instance, this level, steady state level of CO2 depends negatively on K. The larger is K, the smaller is the steady state level of CO2 in the atmosphere. So what happens here? Suppose that we want to intervene on the environment by controlling the level of emissions, okay? What happens? On the left of this steady, if the system is on the left, so if the current CO2 is on the left, smaller than this critical level, it's still possible that the amount of CO2 decreases and in the limit converges to 0. But if we are already on the right, it increases. It tends to increase without any bound, at least according to this simple model, okay? So suppose that we want to control the amount of emissions. So by controlling the amount of emissions, we could reduce the amount of emissions, okay? This would increase this critical point to some point here, for instance, which may be enough to be already on the right of the current level of CO2, okay? In which case, we would have a movement towards decreasing level of CO2. So, I mean, if I decrease K, this increases. Suppose that out of the blue, there is an agreement by which the level of emissions decreases immediately to a much smaller level, okay? Well, this would increase. So it goes, for instance, here. So we have another phase diagram, which is this one, that would converge to another level of K prime, which is smaller, okay? Is that clear? If the current state of the pollution, of the CO2 in the atmosphere is somewhere here, this is enough to to make a good process come into play, okay? Because we would be on the left of this, but this is unstable, and we would have a movement towards a decreasing level of CO2. But if our new level of emissions is such that the new steady state is anyway on the left of the current level of the pollution in the atmosphere, this is not enough, okay? So this is a typical property of unstable steady states. They act as a critical point for dynamical systems. Very critical because they are a kind of threshold between some bad outcome and some good outcome. In this particular model, the good outcome is decreasing the level of CO2 towards zero, and the bad outcome is increasing unboundedly the level of CO2, okay? So this is a very simple model, I mean, based on this assumption that the capacity of absorption exists anyway, but it decreases with the level of CO2 in the atmosphere, okay? So this is the assumption that makes this outcome to become the result of our model. But we may have different assumptions. For instance, an optimistic assumption could be that the level, that the capacity of absorption is somehow increasing function of the level of emissions. This is not very realistic, not of the level of emissions, sorry, of the level of pollution. For instance, y dot, study this model. I mean, this is just a differential equation. K minus delta, delta is like a depreciation rate, times y, or times even square root of y. Okay, delta is positive. Okay, square root of y. Now, we are assuming that this is the level of emissions per unit time, and this is the natural decay rate of the CO2 in the atmosphere, which we assume to be proportional to the square root of the amount of CO2 in the atmosphere. So here we are assuming that the larger is the amount of the atmosphere and the larger is the capacity of absorption of the environment, which is a very optimistic assumption, okay? Is that clear? I mean, I'm not telling you that this is right, that was wrong, just to reason on the assumption and see what happens in terms of the model, okay? Next, you can select the model that you like most, okay? So for instance, this is an example which is taken from the other textbook, Hoy, Livernois, and others, and Stengos, okay? There are many assumptions, many models on, also environmental applications of very simple equations, okay? So this is an assumption, for instance, I don't know because I'm not an environmental economist, of course, but this is a very optimistic assumption in which we may assume that there is some rule by which if the amount of CO2 in the atmosphere is larger, we build more forests and more trees, okay? So this we have a capacity of absorption which in some way is a direct function of the amount of pollution, okay? So in this case, this is just to let you know that in this case the dynamics would be very different, very, very different, because try to represent the phase diagram in this case. For us, mathematically, we just want to solve an exercise, okay? But I just add some economic interpretation which can be useful. Okay, so the square root of y function multiplied by a constant would be simply like this. Okay? Minus square root of y multiplied by a constant would be like this. If we add a constant, a positive constant, it is this one shift upwards by k. It is like this, okay? So this is k qualitatively, k minus delta square root of y. What would be the steady state in this case? The steady state in this case would come out from the equation k minus delta square root of y equal to 0. So the square root of y would be equal to k divided by delta, okay? And the square root of y would be k divided by delta squared. Now, in this other model, which is very different in terms of assumptions from the previous one, in both there is a decay rate, but in the first model, the decay decreases with the amount of pollution. In this one, the decay, the capacity of absorption increases with the amount of pollution, okay? Very different. What happens here? If we increase K, the level of emissions, this is anyway a bad outcome because we get something like this. You see, Y star increases with K. If we increase the level of emissions, the new model is this one, okay? The new steady state. So, the amount at the steady state, the amount of pollution in the environment increases with the level of emissions. But what is the good news for this model? Is that the steady state is stable. So, in any case, we would have here a convergence towards the steady state level of pollution. So no unbounded evolution of the amount of CO2, okay? So I think that this is a very simple example in which we can just think of the assumptions of this model, look at the functions that translate these assumptions into mathematics, and look at the outcome, and try to interpret the outcome without any, select the model that, the models are selected based on the data in the next step of research, okay? But mathematics just tells us that if the model is this one, with this assumption, we have this outcome. If the model is this one, we have a totally different outcome. In any case, the level of pollution, the level of emissions is bad in both models, because in the first model, it moves the threshold upwards, which means that given the current level of in the first model, increasing the level of pollution, increasing the level of emissions, moves the steady state level of pollution downwards, which means that given the current situation of the system, it is more likely that the level of pollution increases unboundedly, okay? So the outcome is bad. In this model, however, the steady state is stable. Increasing the level of emission is still bad because it increases the steady state level of pollution in the atmosphere, okay? Anyway, it is stable, so it is a totally different outcome. There is no threshold effect with this kind of irreversibility, okay? In this case, we don't have this effect. This is what the models tell us, okay? There is an example in the slides here in which I specialize the coefficient to 1/4. So you can just have a look at this. It is exactly what I did basically before with the general alpha. So for instance, a numerical example is this one. Suppose that the model is like this, and determine the maximum sustainable level of emissions as a function of the current stock of CO2, which is Y0, okay? So we want that Y0 is below the threshold, because if and only if the current state, the current stock of CO2 is below the threshold, then we can hope that it converges to 0, because if it is above the threshold, it will start to increase unboundedly, okay? So the steady state will depend on the level of emissions. So Y0 must be less than 1/k to the power of 4, which means that the level of emissions in this example has this numerical value. So, okay, this is just a numerical example. So I want to point out the threshold effect, which appears every time we have an unstable steady state like this. So basically, stable steady states in applied nonlinear dynamics, in applied dynamic models, stable steady states represent the long-term outcome of a system. Stable steady states are the long-run outcome of a system, okay? If you look at the long run, this will be the final situation. Unstable steady states do not represent the long run outcome of a system, because unless you start exactly at the steady state level, the system will move away from the steady state, okay? But they are really important because they represent a kind of threshold between two different long-run outcomes. In this example, one outcome is a stock variable that tends to decrease over time, and the other outcome is a stock variable that tends to increase over time, okay? So stable steady states are, in economics, long-run equilibria. Unstable steady states are thresholds between two different outcomes in the long run. Typically, one is good, one is bad. Okay, this is an important insight also from very simple models. Okay, so this is basically this concludes the part on the qualitative analysis of differential equations. Now I want to briefly introduce difference equations, and I would like to just start from something that I hope is known to all of you, which is the meaning of a geometric sequence and the geometric series. Nobody knows this. How many of you know the geometric sequences and series? Okay, feedback from home? What about geometric sequences and series? Okay? Please, tell me.
Yes, we also see it in the crash course of mathematics.
Okay, so this is the reason why I just want to give you the basic idea of what a difference equation is, because the solution to a difference equation in the most simple case, which is linear and with constant coefficients, is just an application of a geometric sequence. But basically, what is a geometric sequence? You have a sequence of numbers. If you look at this example, you see that these numbers are, at each time step, they are multiplied by a factor of 0.5, okay? So 1 is half 2, 1/2 is half 1, and so on and so forth, okay? So basically, if you take the ratio between any two of these numbers, so you take the ratio between this one and the previous one, immediately preceding one, you get 1/2. If you do the same between this and this, you get 1/2. So the ratio between two subsequent terms is constant. These terms are called a geometric sequence in this case, okay? So what is the mathematical representation of a geometric sequence? Don't look at the plus. Okay, it is, the first term is a number. The second term is a times a factor k. The third term is a times a factor k times again a factor k. So it is times k squared, and so on and so forth, okay? The last term of the sequence, these are n terms, n, it's a times k to the power of n minus 1. For instance, let's say if a is 2 and k is 1/2, the term number 6 is 2 times 1/2 to the power of 5, n minus 1, okay? And in fact, 1/2 to the power of 5 is 1 over, so the sixth term is this one, okay? 2 times 1/2 to the power of 5, which is 1 over 32. it becomes 1 over 16, which is exactly the sixth term here. Okay, so there is a rule to write down the nth term of the sequence based on the first term, on the number of terms, position, and k. K is the common ratio between any term and the preceding one. The first term is usually denoted with A. It is just called first term. I think it's advertising, so it's always active. So let me just put this. Okay, so there is an important application is the sum of the first n terms of a geometric sequence, okay? So there is a formula for this sum. You can look at you can look at the proof, which is here already. It's 2 lines of this formula, but basically, if we know that terms are evolved according to a geometric sequence, and we want to compute the sum of the first n terms, and we know what is the first term, A, and we know what is the common ratio. The common ratio is the constant ratio between one term and the previous one, okay? We have a formula here, which is first term times fraction, common ratio to the power of n, minus 1 in the denominator, common ratio minus 1 in the denominator, okay? So if you are interested in the proof, it is here. It's 2 lines of proof, okay? This is a very important formula. The sum of n terms following a geometric sequence with first term A and common ratio K. So for instance, if we want to compute the sum of the first 6 terms here, of this geometric sequence, we want to take the sum of the first 6 terms. First term is 2, so the sum is 2 times. Of course, I can also write here 1 minus and 1 minus in the denominator because it is exactly the same. Okay, so I usually personally use this one when the common ratio is larger than 1. In this way, I have positive quantity and positive quantity both in the numerator and the denominator. And when k is smaller than 1, I use, smaller than 1 means in modulus, I use 1 minus 1 minus, okay? So here I use 1 minus because the common ratio is 1/2. It is 1 minus 1/2 to the power of 6 divided by 1 minus 1/2. In the denominator I get 1/2. Dividing by 1/2 means multiplying by 2. So the result is 4 times 1 minus 1/2 to the power of 6. It's almost 4. 4 times 63 over 64. It's almost 4. But the interesting property of this particular geometric sequence is that even if you take 20 terms or 400 terms, you get something which is smaller to 4. It's closer, gets closer and closer to 4, but it remains smaller than 4. Okay? Why is that? Suppose that you want to compute not n equal to 6 terms, but generic n terms. You want to take the sum of generic number n of terms. The only thing that would change here would be n instead of 6. The rest will remain exactly the same. Then you have a formula for the sum of the first n terms, which is this one. If you want to see what is the behavior as n tends to infinity, so you want to compute the sum of the first 1 million terms, let n go to infinity, this tends to 0, and the sum is exactly 4, okay? Of course, why is that? Because at each time step, we are halving the amount that we add to the sum, okay? And this is enough to have a convergent value for the sum. Is that intuitive enough? Is that clear? I hope that you can follow me. So we have a formula for the sum of infinitely many terms, provided that it is possible to compute the sum of infinitely many terms. And the formula is first term divided by 1 minus k. Just because this one would tend to 0 in this case, okay? So what is left is a divided by 1 minus k. Would be minus 1 divided by k minus 1, which is 1 divided by 1 minus k. And this happens, so it is possible to compute the sum of infinitely many terms if and only if the common ratio is smaller than 1 in modulus. So if and only if the common ratio of our geometric sequence is smaller than 1 in modulus, which means between minus 1 and 1, okay, it is possible to compute the sum of infinitely many terms, and the result of the sum is first term divided by 1 minus the common ratio. Okay, so basically, here are two more examples just to make things clear. Suppose that you have a geometric sequence which is like this. A is equal to 8. K is equal to 3 over 4. Okay? So the first term is 8. The second term is 8 times 3 over 4 equal to 6. The third term, this is 1. This is 2. The third term would be 6 times 3 over 4. So this is 3 over 2. Okay, 3 over 2, 9 over 2. And so on and so forth, okay? What happens here? It happens that A is equal to 8, K is equal to 3 over 4, so K is between 0 and 1, so in particular it is less than 1 in modulus, it is between minus 1 and 1. What is the sum of infinitely many terms of this geometric sequence? It's just A divided by 1 minus K. So it is A divided by 1 minus 3 over 4 is 1 over 4, 32. Okay? These kind of sums are denoted like this. Sum as and ranges between 1 and infinity of first term 8 times common ratio to the power of n minus 1. Let me see if it works. When n is equal to 1, it is 8 times, this is raised to the power of 0, so it is 1. First term is 8. Okay? When n is 2, this becomes 3 over 4, so we have 8 times 3 over 4, which is this one. As n is 3, we have this one, and so on and so forth. So this is the notation. In general, we can write the sum as n ranges from 1 to infinity of the first term times the common ratio to the power of n minus 1. Okay? This denotes the sum of the infinitely many terms of a geometric sequence, provided that this notation makes sense. So provided that k is in modulus smaller than 1. Otherwise, it makes no sense to compute this sum because there is no convergent sum, okay? It's not possible to arrive at the finite value for the sum. Okay, I want to point out another thing before showing the difference equation themselves. We know that the sum has n ranges between 1 and infinity of, this is the first example, 2, first term was 2 times 1/2 to the power of n minus 1 was equal to 4, okay? This was our first example. So what happens now if k a equal to 2, but k is equal to minus 1/2. So k is negative. So let me try to list a few elements of this sequence. 2 is the first term, minus 1. 1/2, minus 1/4, okay? 1/8, minus 1/16, and so on and so forth. So you see that at each step, the sign changes, and this is a consequence of the common ratio being negative. Anyway, k is again in modulus less than 1. So we should expect that the sum converges to some value, okay? But on the other hand, this is very similar, but it has all the terms with the same sign. So it is exactly the same, but in this case, the terms minus 1, minus 1/4, okay? So this is the second, the fourth, the sixth terms, and so on and so forth, are negative instead of positive. Here we have a sum that converges to 4. What do you expect here? We know that this sum will converge because k is in modulus less than 1. Do you expect that the sum is 4, larger than 4, or less than 4? Here we are taking the sum of all these terms. Here we take the sum of part of them, but part of them are just subtracted, okay? But the terms are the same, so this will be less than 4. Of course, it's very intuitive. Even if it is an infinite sum, it has some properties that correspond to the same properties for finite sums, okay? It will be less, it cannot be larger than 4, because it has the same terms here, but some of them are negative. So what is the sum in this case? Sum is equal to 2 divided by 1 minus k, 1 plus 1/2. Because minus 1/2. Now this is 3/2, okay, in the denominator. 2 divided by 3/2 is 4 divided by 3, which is less than 4, as expected. So remember that when the common ratio is positive, you have all the terms of the same sign. When the common ratio is negative, the sequence displays alternating signs, okay? Positive, negative, or negative, positive, depending on the first term. So this is what we need. Now, I want to show you what a difference equation is. Okay, this is the most simple type of difference equation, which is an elementary model of evolution of some variable in discrete time, not in continuous time. So we consider only the values, for instance, at the end of each month, or at the end of each day, at the end of each year, not at any point in time. And we have some rule by which the value of my variable next time depends on the value at the current time, okay? For instance, this is the value of my variable at the end of the current year, and this is the value of the variable at the end of the next year. So you see there are discrete time steps. Now, depending on the type of application in economics, we may have continuous time models or discrete time models. There is also a rigorous way to switch from one in continuous time to, let's say, a corresponding one in discrete time, vice versa. But keep in mind that in general, the reason why we model in continuous time or in discrete time depends on the type of application. For instance, if there is a model in which you want to use data that are available at discrete points in time, for instance, monthly data, it's quite natural to build a model, a dynamic model in discrete time. If you study population dynamics, infection diseases, or other economic models that are based on the spread of infectious diseases, because there are many of them, marketing models, other kinds of models, environmental models, and so on and so forth, or when the models rely upon an equation for the time evolution of a renewable resource, for instance, fish and whatever, it's much more natural to use models in continuous time, okay? Then, of course, when you rely on data, you always have data at discrete time steps, but it is more natural to model in continuous time, okay? Here, it is natural to model in discrete time just because, for instance, consider a model in which one variable is, let's say, the inflation, okay? So the inflation data are delivered at discrete time step, okay? And also, based on the data that are delivered, people form expectation about inflation next month, okay? So it's quite natural. In this setting, it is quite natural to model in discrete time. Is that clear? It is, but in principle, there is a way to switch from one to the other.
So is the continuous time models used for finance, right?
Yeah, continuous time work also for finance, just because currently, not 30 years ago, but currently, finance is basically continuous time finance, because due to the way financial markets work, it's possible to intervene at each second based on the situation of the previous second, okay? Previous minute or second. So basically it is a model in continuous time, but also in reality it works in continuous time. So, for instance, there are sometimes so-called arbitrage opportunities in financial markets, but they last a few seconds because the automatic trading systems realize that and try to correct that by buying, selling, and okay. So this happens at very high frequency. Okay, so basically in continuous time. But the big difference is that these are deterministic models. Finance is based on stochastic models in continuous time, not deterministic. These simple models are deterministic. There is no additional variables that express, for instance, noise, okay, as a random variable. Continuous time finance is based on continuous time stochastic models. Okay. Okay, so now look at this simple difference equation. This is called linear difference equation, first order linear difference equation with constant coefficients. It has this mathematical expression, the equation, I mean, x at time t plus 1 is equal to a coefficient times x of t plus b, a constant. These coefficients are called a and b, but this a is not the same as a in the corresponding continuous time model, because if you remember the continuous time model, we had x dot plus ax. So basically a was on the left side, okay? Here it is on the right. And also x dot that you find in the continuous time model is not the same as xt plus 1 here. This is a level of the variable. X dot is a derivative. So just keep in mind that they are two very different settings, okay? But basically, this model says that we have the current level of our variable. In order to obtain the next level, just multiply the current level by A and add B. This is called linear first-order difference equation. Solving this means finding the corresponding sequence of terms of our variable at each time, 0, 1, 2, 3, 4, etc. So there is a big difference between the way the evolution is expressed here. It is expressed in recursive terms. I can compute xt plus 1 only if I know xt. Okay? So if I do not solve the equation, I can compute x at time 100 only if I know x at time 99. Okay? If I solve the equation, I have a mathematical expression that depends on t, so I can compute directly the value of the variable at each time step. So the equation is a recursive condition. I have to solve it in order to arrive at the fully displayed formula for x at time t. Is that clear? Let me solve the equation. It's very easy to solve this equation. We can start from the basic model in which b is 0. xt plus 1 is equal to axt. So suppose that initially b is 0. This is very easy because it just tells us that the value of the variable at time t plus 1 is the value of the variable at time t multiplied by a constant. Okay? And clearly, this is a way to state that the terms follow a geometric sequence, because writing down the equation in a slightly different way, so here we have xt plus 1 is equal to a times xt. This is the law of motion, the law that governs the evolution of the variable, given that we have a certain level x0 at time 0, okay? Start with a certain level at time 0, x0, and then the evolution is xt plus 1 is equal to axt, but this can be written as xt plus 1 over xt equal to a constant, a, which means that this is our variable follows a geometric sequence, okay? Now, since it follows a geometric sequence and we have the solution formula for the geometric sequence, we can solve the equation. Why? Because here, the initial value is x0, so what is x1? x1 will be a times x0. What is x2? x2 will be a times x1. But since x1 is a times x0, x2 will be equal to a squared times x0. Okay? What is x at time t? It is a to the power of t times x0. So there is a geometric sequence. It has first term x0 and common ratio a, basically. The solution is a geometric sequence with first term x0, common ratio a. And you can immediately compute the value of your sequence at time t. Even if t is 100, you know that the first term is x0, you know that the common ratio is a, it's x0 times a to the power of 100. Okay? So this is the solution to our difference equation. What is slightly more difficult is the full model, in which at each time step you don't only have, okay, that xt plus 1 is a times xt, but possibly plus b. So basically there is an endogenous part of the evolution by which xt plus 1 depends on xt, but there is also some forcing exogenous part, which is plus b, okay? So at this time step, we intervene in the endogenous evolution by adding B. What is the final outcome to this process? We can follow the same steps. This is a kind of inductive approach, okay? We try to compute the first terms and guess what the general formula could be. So x1 is equal to, look at this, if t is equal to 0, x times 1 will be equal to a times x0 plus b. This one. If t is equal to 1 now, x at the next step, x2, will be a times x1 plus b. x1 is this one. So replace a times ax0 plus b. It becomes a squared x0 plus ab plus b. You can do the same for x3, which is ax2 plus b. You see the recursive formula here. x3 is computed in terms of x2. But x2, from the previous step, is a function of x0. So you can substitute here, and you get this one, a to the power of 3x0 plus a to the power of 2b plus ab plus b. It's not difficult to figure out what xt would be. It is x0 times a to the power of t plus b that multiplies 1 plus a squared plus a to the power of 3 plus a to the power of t minus 1. Okay? This is the sum of a geometric sequence. The first term is 1. Common ratio is a. So the content of this green parenthesis here is 1 minus a to the power of t divided by 1 minus a. Okay? Which has to be multiplied by b. So basically we have the solution formula, which is x at time t is x0 times a to the power of t plus b that multiplies the sum of that geometric sequence. 1 minus a to the power of t divided by 1 minus a. You can split this fraction in two parts, 1 over 1 minus a and minus at over 1 minus a. Multiply both by b and you get this formula. Then you have two terms that include a to the power of t, which is this one and this one. So you factor these two terms, a to the power of t times x0 minus b over 1 minus a plus b over 1 minus a. So it has a very interesting structure. It is a constant b over 1 minus a that you will see in a moment represents the steady state solution to the difference equation. And the other part is the deviation between the initial value and the steady state solution. And this deviation between the initial value and the steady state solution is multiplied by a factor a to the power of t. So let me just rewrite in another slide the formula, show you why this can be interpreted as a steady state solution, and show you the interpretation of this solution here. It is already, everything is already in the slides, but I prefer to rewrite this and to focus on this. We know that if we have this equation, which is discrete equation, so it's a difference equation. Or it is called also a recursive equation. X at time t plus 1 is a times x at time t plus b. This is the equation. Equations have solution. The solution of the equation is not, this is just the law of motion. But if I want to arrive at a solution, I have to specify an initial condition, so an initial value for the variable. This is the equation, this is the solution. X at time t is equal to x0 minus b over 1 minus a, which is called x star, because it represents a steady state, times a to the power of t, plus b over 1 minus a, which is again x star. Okay, why is b over 1 minus a steady state? Okay, remember that a steady state is by definition a constant solution to our difference equation. A steady state solution is a constant solution, so it is a sequence that satisfies the difference equation, but it is constant. It always remains at the same level. Okay? If I want to find a steady state, I must impose that my variable in the solution remains at a constant level. Okay? Call this constant level x star. So x at time t plus 1 will be again x star when x at times t is x star, okay? So if a solution has to be constant and at time t it is at the level x star, it must remain constant also at time t plus 1. So it must be at the level x star also at time t plus 1. Otherwise it is not a constant solution, okay? So if there exists a constant solution to our difference equation, it must satisfy this condition. But now I can solve for x star, because it becomes x star, it becomes x star times 1 minus a equal to b. So x star is equal to b over 1 minus a. Okay? So for instance, example. Numerical example. Suppose that you don't know the solution formula to the difference equation. You have this difference equation, which is xt plus 1 is equal to 1/2 xt plus 3. So see what happens at each time step. Suppose that you start from the level x0 equal to 8. So what is x1? It is 1/2 8, okay? Because t plus 1 is 1, so t is 0. So x1 is 1/2 times x0, so times 8, plus 3. So you start from 8, but the next level of the variable will be 4 plus 3, 7. Now, what is x2? It is 1/2 times x1, this is x0, okay? Now, x2 is 1/2 times x1 because it is a recursive relation. A value given the value of the preceding period, okay? So it's 1/2 times 7, which is x1, again plus 3. So this is 3 over 5 plus 3, 6 over 5, and so on and so forth. If you go compute x3, x4, you see something happening here. You see that it decreases from a to 7. Here it decreases by 1, but next it decreases by 0.5, 6.5, and you see that it decreases, but of a smaller and smaller amount. It tends to approach something. What is this something? This something is the steady state. How can we compute the steady state? Suppose that we don't know what is the solution formula, but we wonder whether there exists a constant solution to this equation. If there exists a constant solution, xt plus 1 must be equal to xt at any time t. okay? So this means that xt must be constant at some level x star. Put x star into the equation, so impose that at time t plus 1, the level will be the same as at time t. So x star equal to 1/2 x star plus 3. Okay, so move this to the left. X star times 1 minus 1/2 equal to 3. This is 1/2. So x star is equal to 6. Okay? So there exists a steady state solution. If you start from the level 6 instead of 8, like here, try to start at the level 6. If the x0 is 6, this becomes, what is x1? 1/2 times 6, 3 plus 3, 6. It is again 6. So at time 1, the level of the variable is 6. What about time 2? Time 2 will be 1/2 6 plus 3, 6. It will remain constant, okay? This is a steady state solution. Suppose that we don't start exactly from the equilibrium value, the steady state value. We start larger than this. But our numerical example here shows that we tend to approach 6, okay? So in this case, not only 6 is a steady state solution, but is also stable, okay? It is also stable. So we tend to approach this steady state level in the long run. Why is that? Go to the solution formula. We know that for this equation, next page, the solution formula will be xt is equal to, remember the formula, it's x0 minus x star, where x star is b over 1 minus a, okay? Times a to the power of t plus x star. Replace our numbers. X0 is 8, okay? Okay, 8 in our example, minus 6. What is 8? 1/2. It is between 0 and 1. It is less than 1 in modulus to the power of t plus 6. I want to be slightly more general, so it is x0. x0 is 8 in our case, can be any initial level, minus 6 times 1/2 to the power of t plus 6. What happens as t tends to plus infinity? What happens in the long run? We have two parts. The steady state part, which is a kind of long run component of the solution, and the transitory part, which is initial deviation from the steady state multiplied by a factor 1/2 to the power of t. What happens to this factor as t tends to infinity? 1/2, 1/4, 1 over 8, 1 over 16, 1 over 32, 1 over 64. It tends to 0. Okay, so the factor tends to 0. The initial deviation is multiplied by a factor that tends to 0. It will disappear in the long run, okay? So the limit as t tends to plus infinity of xt, our solution, will be equal to 6. So it will be equal to the steady state. Okay? This is a property of this is basically a property of the geometric sequences by which if I have a term, a common factor, which is less than 1 in modulus, okay, when I raise this to an exponent t that tends to plus infinity, this goes to 0. So this is basically the main message from the behavior of the solution to that difference equation. Okay, so I go back to the slides. This is the structure of the solution. B over 1 minus a, which is x star. That's the long run, let's call it long run steady state level. The equilibrium component and the transitory component. The transitory component is the initial deviation from the equilibrium, from the steady state, multiplied by a factor a to the power of t. The point is that if a is between 0 and 1, or between minus 1 and 1, it's something that decreases as t increases, okay? It tends to 0, so that initial deviation will disappear in the long run. However, if A is 2, for instance, what happens to this initial deviation? It becomes amplified over time, okay? Like for differential equations, exactly like in the case of differential equations, okay? You may remember that in the case of differential equations, we wrote this, x dot plus ax was equal to b, okay? And the solution was xt equal to x0 minus x star times exponential minus at plus x star, where x star, based on the parameters of the differential equation, x star was equal to b over a. Okay? Now look at the structure of a somehow related, it's not related at all, but at least in principle we can compare them. Xt plus 1 is equal to axt plus b. Here a has a totally different meaning, of course. We know that the solution xt is x0 minus x star times a to the power of t plus x star. You see that the analogy, there is some long run component. In this case, if a is positive, minus a is negative, in the long run, this part will disappear. This part is the initial deviation from the steady state multiplied by a factor that disappears in the long run if a is positive, but it grows in the long run if a is negative, okay? Here we have a similar structure. The solution is this one, a steady state part, a part that depends on the initial deviation multiplied by a factor. This factor disappears in the long run if a is in modulus less than 1. But if a is larger than 1 in modulus, this grows in the long run, okay? This is a very similar insights from the solution formula of the two cases. Of course, a has a very different meaning here and here. It's a different parameter, basically. Okay, so it's written all here. If a is in modulus less than 1, that is a between minus 1 and 1, then the limit of the solution as t tends to infinity will be x star for any x0, for any initial level of the variable. In this case, we say that the steady state x star is globally stable. The meaning of global stability is the same as for continuous time models, okay? So there will be, the final outcome will be x star, and this is independent of the initial condition, okay? However, if a is in modulus larger than 1, the steady state is unstable. Why? Because this one will explode over time. Because you see, it is an exponential, okay? The variable is at the exponent. The base is something which is larger than 1 in modulus. So this term grows exponentially. So this deviation will not disappear in the long run. It will be amplified in the long run. There are two particular cases left when a is equal to minus 1 or is equal to 1. But before showing these cases, I want to show you another example with a negative a okay. So let me start with x0 equal to, for instance, 16. x1 will be equal to minus 1/2 times 16 plus 2. Okay? So minus 1/2 times 16 is equal to 8. 8 plus 2 is equal to 10. So the x1 is equal to 10. X0 is equal to 16. Now see what happens. X2 will be equal to minus 1/2 times what? Times 10 times x1 plus 2. This becomes...
Professor, might be minus 6.
Sure, there is a minus sign. It's minus 8 plus 2, it is 6. Clearly. Sorry for that. I didn't consider the minus, of course, which is the most important thing. Thank you. Thanks a lot. X2 is equal to minus 1/2 times 6. Okay? This is minus 8 plus 2 minus 6. Okay? Is that clear? Minus 8 plus 2 minus 6. This is minus 1/2 times minus 6 plus 2. This becomes 3 plus 2 is equal to 5. Okay? So it starts from 16. It jumps down to minus 6. Then again up to 5. Okay? X3, please intervene if I make further mistakes, more mistakes. This is equal to 5, so x3 will be equal to minus 1/2 times 5, okay, plus 2. So it is minus 5 over 2 plus 2, so it is equal to what? Minus 5 over 2 plus 4 over 2, it's minus 1/2. So you see what happens here. Starts from 16, jumps down to minus 6, up to 5, down again to minus 1/2. So what's happening here? It jumps down and up, but anyway it approaches something which is in between, okay? So what is this something in between? It is the steady state. What is the steady state to this equation? We can compute it because it's b over 1 minus a. A is this one, b is this one, okay? The steady state x star is b over 1 minus a is equal to, b was 2, right? Divided by 1 minus 1/2. 2 divided 3 over 2, which is equal basically to 4 over 3, okay? So it approaches some level which is 4 over 3. So if you want to, I mean, if I'm not sure I didn't make any mistake. Did you check my computations before? But anyway, qualitatively it is like this. It starts from 16. Something here, okay? Time 0, start from 16, jumps back to minus 6 at time 1, more or less here, okay? So this here is time 1. Time 0 it is here, the system, at time 1 it is here. Then at time 2 it jumps up again to 5, okay? So 5 is something about here. Time 2, it is again here. Time 3 it jumps to minus 1/2, which is somewhere here. So you see what's happening here. It goes like this. Okay? It's a motion by which we have down, up, but it approaches something which is 4 over 3, okay? It is 4 over 3, which is the steady state level in the long run. So basically, this is a qualitative behavior of the solution to this difference equation, and this is what typically happens when we have a negative coefficient A. However, here it is negative, but in modulus, it is smaller than 1. So we have convergence to the steady state. If A is smaller than 1 in modulus, between minus 1 and 1, our steady state is globally stable. However, if A is positive, okay. If A is positive, we have an example of, say, monotonic convergence. But if A is negative, we have jumps up and down. So here are two more examples. Xt plus 1 is equal to 1 half xt plus 3. Compute the steady state. B over 1 minus A is 6. The solution is 6 plus x0 minus 6. Probably it is the same example, I don't know. X0 minus 6 times 1 half to the power of t. If, for instance, x0 is equal to 1, x0 is equal to 1, this becomes minus 5. So the solution becomes 6 minus 5 times 1 half to the power of t, and the steady state is globally stable, okay? And we can realize that the steady state is stable because A is 1 half, so it is less than 1 in modulus. Here is another example. If I have a difference equation here, which is written in this way, xt plus 1 plus 3 over 4xt is equal to 7. It's better to rewrite this in a form in which only xt plus 1 appears on the left, and we realize that now our coefficient A is negative, okay, it's minus 3 over 4. Anyway, it is less than 1 in modulus, so our steady state will be stable. What is our steady state? B over 1 minus A, 7 over 1 minus 3 over 4, which is 4. If, for instance, x0 is equal to 2, the solution formula is x0 minus x star is 4, times A to the power of t, A is minus 3 over 4, plus x star. So put 2 here, becomes minus 2. So this is the solution formula, okay? Now, I have uploaded slides. This is the most important cases. I have uploaded slides with an extended version of this part on difference equations. I just use them to show you the solution graphically in some cases. So basically, everything is repeated again here. It is a slightly wider perspective, but anyway, don't worry. Just it is enough what we saw here already. But what is important in this extended set of slides is the representation. Okay, so this is the representation of the first equation that we studied. Okay. In the first example, I started, I remember, from 8, okay? But if you start, for instance, from 1, and you try to represent the solution formula, you see that the solution formula converges to the steady state. And the reason why the time path converges to the steady state is that the coefficient A is less than 1 in modulus. In particular, here it is positive. So less than 1 in modulus means convergence. If it is also positive, means monotonic convergence. Monotonic means if I start below, I will remain below, but I will approach the steady state. If I start above, I will remain above, but I will approach the steady state. But if it is negative, then convergence is non-monotonic. And here is the example with the second equation we studied in the previous set of slides. Okay, 4 is the steady state, but you see a non-monotonic convergence to the steady state. Okay, and the reason is that we have A, which is negative, so we have at each time steps, jumps above and below the steady state level. However, the size of the jumps decreases exponentially over time. The size of the jump, okay? And the size of the deviation from the steady state decreases exponentially over time. So you see something like this. So there is a big, why in the long run we have a steady state in both cases. Here there is a big difference in the transitory behavior. Because what happens here is a monotonic convergence. What happens here is a non-monotonic convergence. So it's like the system has in mind that its long-run outcome is 4, but it converges with mistakes at each time step, okay? So this is called in economics overshooting, okay? It's called overshooting. At each time step, it overshoots the movement, the correction overshoots the steady state level, okay? It corrects too much in downwards or upwards, but at each time too much, okay? So this is a non-monotonic convergence to the steady state. So I mean, if this represents an economic model and this is some target level of the variable, this is not really desirable, okay? Transitory correction mechanism, okay, to the steady state, while this is desirable, okay? This is a monotonic convergence. This is a convergence that makes overshooting at each time step. And this depends on the coefficient. Negative here, positive in the other example. Now I suggest to stop for a few minutes, and next I will show you examples of divergent behavior. And let's see what else happens. Okay, so let's stop for a few minutes. Okay, we take a break for a few minutes.
Professor, may I ask you something?
Yes, sure.
So the last differential equation we saw, the last model, we had the time derivative of y equal to k minus delta square root of y.
Okay. I see. The nonlinear one, the graphical,
yeah.
the graphical solution. Okay.
I was wondering, the absorption capacity was k.
No. K is in this interpretation. I mean, the K is just the level of emission, the intensity of emissions. It's not the absorption capacity.
Okay, so is that a flow?
Let me go back to the equation. One moment. Is that this one?
Yes.
Or also the previous one? Okay.
Only this one.
The time derivative of the stock of pollution depends on the level of emissions, positively, K, and it has also a negative component, which in principle depends on the level of the stock itself, okay? So this is one way to model the absorption capacity. And in the previous example, we have another way to model the absorption capacity. Underlying this mathematical formula is the assumption that the absorption capacity decreases with the level. It is positive, but it decreases with the level of the stock of pollution in the atmosphere. It's the stock, okay? In this example, the second one, the underlying assumption would be that the absorption capacity is itself increasing in the stock of pollution, okay? They are two very different perspectives.
So the absorption capacity, just to understand, is the time derivative.
No, the absorption capacity, I mean, the time derivative depends on two components. There is some force that tends to increase the stock of pollution and some force that tends to decrease the stock of pollution. The one that tends to decrease is the absorption capacity of the environment, okay? If you imagine that you stop your emissions, you stop K is 0, the evolution is y dot is something negative, okay? Because if you leave things as they are, in the long run, you can expect that there is some absorption capacity of the current level of pollution, okay? But instead, we have also emissions. So this is a positive component of the time derivative, and this is a negative component of the time derivative. So the emissions is a positive component of the time derivative of the stock of CO2. The absorption capacity is a negative component of the time derivative of the stock of CO2, okay?
Okay, thank you.
Welcome. Okay, let's stop for a few minutes. Okay? Let me continue with these difference equations. Let me share the screen. So here is another example of so-called divergent behavior. If you look at the equation here, you see that xt plus 1 is equal to 3 over 2 xt minus 3, okay, minus 3. So first of all, let me compute the steady state. Let me do that. Let me do that as an exercise here. It is already in the slides, but let me do that. Xt plus 1 is equal to 3 over 2 xt minus 3. Okay. Let me, x0 is equal to, let me see, x0 is equal to, for instance, 8. Okay? Write down the solution formula and try to represent graphically the time path. Write down the solution formula for a general x0 and for x0 equal to 8, and then try to represent the solution path, okay? Graphically. Okay, so this is A and this is B. It has a steady state which is equal to B over 1 minus A, that is minus 3 over 1 minus 3 over 2. That is minus 3 divided by minus 1/2, that is 6. Now, what is the solution formula? Xt is equal to, remember it has a component which is the steady state, 6. Then the initial deviation from the steady state, x0 minus 6, multiplied by a factor which is a, 3 over 2, to the power of t. What happens here? Suppose the system has x0 equal to 6. If x0 is equal to 6, the initial deviation from the steady state is 0. This is a very, very particular case. 0, and it is multiplied by 3 over 2 to the power of t, but it becomes 0. If we start from x0 equal to 6, the system will remain at 6 forever. But this is the only case. If we start from any other x0, we have an initial deviation here, positive or negative. What happens to this initial deviation? It gets amplified over time. Because this is 3 over 2, at time 2 it is 9 over 4, 27 over 8, it grows exponentially. So the initial deviation explodes over time. So in the solution, we have a divergence, not convergence, divergence. However, this divergence is monotonic because 3 over 2 is positive. So this is a case of monotonic divergence. Now, another thing, of course, if you want to figure out what the first values of your sequence are, you have the difference equation here, the solution here. In this particular case, when x0 is equal to 8, this becomes 8 minus 6. So 2 times 3 over 2 to the power of t plus 6, okay? You can compute the first numerical values of your sequence in two different ways, of course. One, from the solution, using this formula. At time 0, at time 1, at time 2, put t here, okay? And one, with the recursive equation. Start from x0, which is 8. x1 is computed as a function of x0. x2 is computed as a function of x1, okay? You get the same sequence, of course. So, for instance, if you go back to the slides, we want to compute the first three terms of the sequence. x0 is equal to 8. x1 will be equal to 3 over 2 times 8, which is 8 divided, it's 12, minus 3, it's 9, okay? On the other hand, if you go to the solution formula, x1, put 1 here. If you put 0 here, this becomes 1, and you get back 8, okay? If you put 1 here, 2 times 3 over 2, which becomes 3, plus 6, equal to 8, okay? Now, the third term, x2. x1 is 9, so 3 over 2 times 9 minus 3. 27 over 2 minus 3. 21 over 2, which is 10.5. But you can do the same using the full solution. Put 2 here, 3 over 2 to the power of 2, sorry. It's 9 over 4, so you have 18 over 4 plus 6. 18 over 4 plus 6 becomes 18, sorry, this becomes 3 over 4, okay? So 9 over 4. 18 over 4 plus 6, what is 18 over 4 plus 6? It is 18 plus 24 over 4. 18 plus 24 over 4 is 42 over 4, which is 10.5, okay? So remember that if it's just a matter of computing the first elements of the solution sequence, in principle, you don't need to solve the equation. You don't need to arrive at the solution formula, because you can compute the first elements of the sequence also recursively based on the difference equation. You have the first one, then you compute the second one, the third one, and so on and so forth. Of course, if you have the solution formula, you can immediately compute all the terms, okay? Is that clear? What is the behavior here? The steady state is 6, however, the initial level of the variable is 8, the next level is 9, 10.5, 51 over 4, and so on and so forth. You see a kind of exponential movement away from the steady state level, okay? And this happens because 3 over 2 is larger than 1 in modulus. Clear?